So this is chapter number 9. It's about the capacitors, girls, and it's inshallah it's gonna be some, you already know some information about the capacitors, so you can easily understand this chapter. Okay, so starting with the basics of the capacitor. So what is a capacitors? You know that there is a two conducting plates, okay, and in between that we fill a dielectric, or dielectric yani what we call insulator. It could be a air, it could be some dielectric material we filled here. So capacitors are one of the fundamental passive components. Like you know that components are active and passive, two type. So conductors are passive component, or as well as inductors is also there, which is also passive component. Okay, resistance is also a passive component. So in its most basic form, it is composed of two conductive plates separated by an insulating dielectric. The ability to store charge is the definition of the capacitor. So capacitance is what basically it can hold the charge on the plates. So see what happened. The basic capacitor is basically when it is uncharged, because of these are made up of which material? They are made up of material basically, conducting material. So they have charges at no room temperature. So initially uncharged. So you will see there electrons are there, protons are there, same time positive and negative ions are there. But it is when it is uncharged. What happen if we connect the battery to it like this? So if we connect positive terminal of the battery to this side and negative to another side via a resistance here to control the current flow, so what will happen? The electrons from this side start attracting towards the positive terminal, and the electrons which is from the battery is gonna attract towards this terminal. Okay, because it will this process will start. So after some time what will happen? The capacitor will be fully charged. Okay, getting point? So initially what was happening when this was not charged? So it was allowing to flow the current through it. Basically you can see this one. Okay, so charge start, you can think in a way like we have a glass, okay, and we are filling with water. So like glass keep collecting the water until it's full. So same happening here. So it's keep on charging until it's completely charged. So when it's fully charged, what will happen? There is a wall of positive charges here. There is a wall of negative charges here. So what will happen now? Further, it will not allow to cross the current through it. And initially, what was happening? The current was, flowing here this way. This way, it was allowing flow current. That's why it is there in the outer circuit. Otherwise, if there is no complete path, there will be no current flow. But it was flowing because of it is initially uncharged. But once it is charged, so it will stop the further flow of current. So it will not allow to pass the charges here, yani no current here, because of it is fully charged and created a wall of charges. So you can see that what will happen, because all are positive charges, so positive will repel each other. We know that similar charges repels, dissimilar attract. So here is a negative, this is a negative, so no electrons can go here because of there's a wall of electrons. So this will repel it, okay, because of the repulsion. So once it's fully charged, there is no current flow. Now, so once it's fully charged, so here the charges is positive, this become negative. You know what will happen if I remove this battery now? Okay, if I remove the battery, so because of this plate is fully positive, this plate is fully negative. So what will happen? It can behave like a temporary battery, because charge is positive, charge is negative. So it can behave like a temporary battery. Why temporary? Because these charges are not forever. It will decay with the time quickly. So it can behave like a battery as a temporary. So if I connect any load or bulb or resistance, it will quickly decay actually. So the capacitor will store charge can act as a temporary battery, but it is not long lasting. You just connect any load, so quickly charge will finish. Okay, so some basics again, you know already these formulas. So capacitance is the ratio of the charge to the voltage. So C is equal to Q over V, and you know already the unit of the charge and the voltage and capacitor. So this formula could also be written as Q is equal to C into V. So C is the capacitor and capacitance, and V is the voltage. So based on that, we can ask a question simply. If 2 microfarad capacitor is connected to 10 volt source, the charge is. So based on this formula, Q is equal to C into V. So V is 10, 22 microfarad is this one. So you need to just multiply those. So 22 multiplied by 10, you will be getting to 20 micro, because of the charge, na? So micro coulomb will be the unit here. Okay. Okay, see, what I said, I asked you, no one replied. So I have started now this one. So let me finish up now. I will give you time later on. I asked, do you have question? But no one replied to me. So definitely I have to cover the topic also. How long I can wait? So just let me finish this one now. Maybe half of the lecture, then I will give you time. Okay. Now, so this is a capacitor. Now, so now let's see the question. This one, a certain capacitor stores 50 microcoulomb when 10 volts are applied. What is the capacitance? So same formula this time, Q is equal to C into V. So I can say now C is equal to Q over V. So you can solve this one again. So this is so simple and you can easily calculate that one. Again, this one. So these questions are so simple directly. You know already, it's kind of review which you will learn already. Now, guys, second thing is the capacitor stores energy in the form of electric field. I told you how this capacitor stored the energy. It is stored the energy in the form of charges, or what we call electric field, because of it is positive and negative. That is established by the two opposite charges on the capacitor plate. The energy of the charge capacitor is given by the equation. So we can calculate the energy, how much it is storing by this equation. So either you can say W is equal to half CV, or if you want to use E, you can use the energy of half CV square. So it's so simple to memorize, half CV square. Okay, this is the energy. So see where W is energy in joules, capacitance in farads, and voltage is in volts. Second thing is about the capacitance of the capacitor depend upon the three physical characteristics. Okay, now what are the characteristics? You can see C is equal to 8.85 into 10 power minus 12 femto per meter, farad meter, and this is epsilon R A over D. You know this one. This is the area of the plates. This is the distance of the plate, and this is epsilon, yani relative permittivity of the dielectric which is filled in the between the plates, right? You know these things. So from this relation, we can say capacitance is directly proportional to epsilon R. Capacitance is directly proportional to the area, right? More area, more capacitance. And it is inversely proportional to the distance between the plates. The point is less than distance, more the charger. Okay, charges your capacitance like that. So this is something which you can know, and you know these formula already. So this is something. Okay. Okay, now sir, this is a series capacitor which could be new for you. So now we can have a circuit in which we have many capacitors. These are connected in series. So when capacitors are connected in series, the total capacitance is smaller than the smallest one. You know what is this here? It is gonna be opposite concept which you learn for the resistance. Like in resistance, when resistance are connected in series, so it will increase or decrease total resistance when they are in series?
Increase.
Okay, increase, right? Okay, also when the resistors are connected in parallel, what will be the total?
It will decrease.
Decrease. So same happening here with the capacitor, but it is opposite now. So this is series. This is series. So we have smaller and smallest one. Yani this is the same concept with the resistance when it is connected in correct. Okay, so this way you can easily understand. The concept is gonna be here opposite. What you learn for the resistance, here you need to think opposite. Yani in series resistance increase, but sorry, in series resistance increase, but capacitance decrease. And this follow the same law as resistance are connected in parallel basically. Okay, so now it's so simple to understand. See this formula. If you remember, the formula when the resistance are connected in parallel is applicable here. You know, it is similar type here with the capacitor. So total capacitance is the sum of the reciprocal of the sum of the reciprocals. Clear? So first you need to, you already know these things, but the formula which was for the parallel in the for the resistance here is for the series. This is you need to understand this. And now based on that you will know a lot of things now, like when two capacitors are connected in parallel, sorry, series. So you can, you know that already when two resistors are in parallel, so what we have the formula product over sum. We use R1 R2 over R1 plus R2. Remember, same when they are in series we can write it down. So we can say C1 C2 over C1 plus C2. So this is interesting and easy to memorize basically. Okay, so this way you can just memorize it. Okay, so this is something, or we can also write product over sum rule, which you already know. Okay, so see now based on that it's so simple. So this is C1 C2, they are connected here. You can see they are in series. We can say they are connected, you know, end to like that, one end to another one. So I need to find their parallel combination. So you can see their, you know, units are different. We need to have a same unit, then we can just put it or not. So you can write micro 10 power minus 6, pico 10 power minus 12. Is it 12 for the pico? Yes. So you can get
Yes.
the, yeah, you can simply get the answer. It's so simple, you can easily get it. Yeah. So this is something. Now, series capacitors. Again, continuation, girls. So now, do you remember when capacitor resistance are connected in series? So voltage divider formula is applicable for that. Voltage divider formula is applicable. Similarly, here we have voltage divider formula. Correct. So the voltage across each capacitor in series connection depends on its capacitance value according to the formula. You can determine the voltage across any individual capacitor in series with the following formula. So what is this formula? Vx equal to Ct over Cx Vs. Ct is what? Total capacitance. So you need to calculate the total capacitance first, divide by the capacitor in which you want to calculate the voltage. So it is basically the general formula. Understand? When we go for the specific, it is gonna be similar to the one which we have for the resistance. We'll see that one. And so what is that? Vx is equal to Ct, total capacitance, over Cx Vs, where any capacitor in series such as C1, C2, C3 and so on, and Vx is the voltage across capacitor Cx. So larger value capacitor in series connection will have the smallest voltage across it. The smallest value capacitor will have the largest voltage across it. We know already when smaller value capacitor, so he will be having larger voltage. It is because of the concept which you know for the resistance here is opposite. We know that smaller value resistance will have larger voltage, but here, smaller value resistance have smaller resistance, but here smaller value will have larger voltage and larger will have smaller voltage. We can see from this formula itself because it is in the denominator. So if this value is lower, you can see, so Vx is gonna be higher, correct? If this value is higher, yani Cx value is higher, so this value is gonna be lower because of the formula. So this fact is verified from this formula itself. Now, so see, capacitors are connected here in series. We can see this is a series circuit, voltage 25, asking find the voltage across each capacitor. So in order to apply that formula, we need to find first total capacitance, and total capacitance we can calculate by 1 over sum of the reciprocal, or then after getting the total capacitance, we can just put it there. So this is total capacitance. Then CT over C1 Vs. Put the values, get the voltage. V2, V3, and you can see. So you can see that C2 is the, look here, larger capacitor, and see the voltage across it. Smallest. Okay, smallest. And this is the smallest one, and see the voltage across this one. If you add these voltages, you will get 25 because it is a series connection. We know that. So voltage will drop accordingly, some here, some here, some here, and you can calculate that one. Clear to all of you?
Yes, that's clear.
Okay. Okay, so two series capacitors, one microfarad and the another is unknown. Okay, we have two capacitor, one is 1 microfarad and another one is unknown value, are charged from 12 volts. So they are charged from 12 volts source. The 1 microfarad capacitor is charged to 8 volts and the other charge to 4 volts. Total charge is 8 plus 4 is equal to 12. So one charge, one microfarad, 1 microfarad charge to 8 volt, but the unknown, which is here, we can say, let's suppose Cx, okay, what is the value of the unknown capacitor? How can we find it now? So what you have given, one capacitance is given, another is unknown. Vs is given to you. And what is given to you? V1 is given to you. V2 is not. So we can say this is V2, C2, and this is C1, for example. So V1, V2 is also given. They are asking you what is the value of C2. So how can you find it?
We should find CT.
CT. Okay. How can you find CT?
Using the V1 because we already have everything else.
Okay. So the formula is gonna be V1 is equal to CT over C1 multiplied by
VS.
Okay, correct. So we can get CT this way. This is gonna be V1 C1 over Vs. Okay, so V1 is, how much is the V1? 8 multiplied by C1. This is 1 micro over, what is that? Vs, yani 12. All right. So how much it is coming? 4 over 3, 2 over 3. 2 over 3 microfarad. Okay, let's say 2 over 3 microfarad. So now you have CT. Then what next?
We will divide CT from C1.
CT from C1. No, why
No,
you want to do?
No.
So we got it one more thing, which is CT now. So now you have CT. Okay. And what you have? You have also V2. So can we apply the formula? V2 is equal to CT over C1 multiplied by Vs. And we can say C1 is equal to CT over V2 multiplied by Vs. Can we say it?
Why is it opposite?
Okay, C2. We need C2. Okay. So what is gonna be then? So this is 2 by 3 over V2. V2 is 4 multiplied by Vs, which is 12. So it will go 4 times, and this 4 will cancel this 4, and value is 2 microfarad. Okay, clear now?
Yes, clear.
Yes.
Okay, so this is the way basically to calculate. So bus formula you can just put here, there, and you can simply calculate it. So this is the way to solve this type of questions. Now, another thing is parallel. So for the parallel, girls, again, okay, 1.98 is almost 2. Yeah, it's okay. So parallel capacitors. So now what you learn for the series resistance, it is applicable for the parallel capacitors. Like when capacitors are connected in parallel, the total capacitance is the sum of individual capacitors. So it's just gonna be same like resistance in series bus. So CT is equal to C1 plus C2 plus C3 like that. So now this is the formula. And by the way, just coming to one here, do you remember the voltage divider, current divider formula for the resistance, girls?
Ix equal Rx over R total.
Right? Do you remember the general formula for the current when current is currents are there in parallel circuit, which is something like that. IT over no, what is that? RT over, yeah, it is gonna be same, basically. So this is gonna be like that. So this is the current divider of type of formula. Definitely for the current we don't have voltage. It is gonna be the replaced with that one, and CT and is gonna be replaced by the resistances. You know that one? Yeah. What is that? RT over, yes, correct. So it is gonna be like that. It's same exactly if you go for the general formula. Okay, so this is gonna be Ix. Yeah, what you write, you are right. Alpha. So it is gonna be like that. So RT over Rx multiplied by IT. So bus we replace R by C and we replace I by V. This is the, because as I told you, what you learn for the resistance, here it is gonna be opposite. So this way you can easily memorize, and it is better if you keep noting here. If you write a note here for your reference, it is similar to the general current divider formula for resistive circuit. But this is so easy for you. You can keep writing the notes here. Okay, so this is done. Now for the series. So it's so simple. When the resistance capacitors are in parallel, same formula. And see the question. It is gonna be very simple. When they are connected in parallel, total is gonna be just sum and get the answer. Correct. This is just add because of parallel yani it is similar to the series bus. So this is very easy here. Now see the question. So what is the total capacitance? Okay, so total, yani add 230 and 330, 220, okay, 550. Answer, see straight. Now, what they are asking, what is the voltage across each capacitor? Girls, it's again so simple. Is this a parallel circuit or not? So,
Yes,
and we know that in parallel, voltage is always same, the basic. So, it is gonna be just same. But current will be different. So, current we can calculate by the formulas. We know that, okay, this is the Weber's. All right. Now, the interesting thing is the RC time constant. You know, in the capacitors, we not only have a capacitor there, sometimes we have resistance also to control the current. So if we have resistance and capacitor in a circuit, both, so we call RC circuit. And RC time constant is what basically, now this is a switch, girls, and you know, as long as it's open, so there is no current flow. So I am going to show you this graph, how it is going to be drawn when we close it. And I told you, you can consider capacitor as an empty glass, correct? So as long as this is, what is that, empty, it's keep filling, it's allowing to flow the current through it, okay? Once it full, it creates the wall, barrier. So it will not allow to flow the current. So what will happen, you will see as I close the switch, look. So as I close the switch, upper one is the voltage developed across the capacitor. See, initially the voltage across the capacitor is 0. And as I close it, it allows the current flow. As the current flow here, so voltage across this start building exponentially. See this one. And when it is completely filled, it say no current will pass. No current will pass. So initially high current was flowing. See, this is the initial current which was high. And with the time it's keep on reducing as the capacitors keep on charging. One capacitor is fully charged, current reach to 0. Yani no current will flow once the capacitor is fully charged. Is it clear to all of you? Easy to
yes.
understand concept?
Clear.
Okay, so it is just a concept, as I told you. When it is fully charged, it's keep allowing the flow of current through it, and when the current is passing through the capacitor, the voltage across that one is keep building exponentially. All right, and current keep decreasing exponentially. Fully charged, yani fully current 0. No current will flow at all once capacitor is fully charged. Okay, do you remember the situation when there is no current flow in the circuit? In which situation current will not flow? Generally, if I ask you, when the
When
when
it's
the circuit
open,
open, absolutely right, absolutely right. Yani it is similar to that. If I remove the capacitor here, so there will be no current flow. So, you know, when capacitor is fully charged, it behaves like what?
An
Open circuit. It behaves like open circuit. When it is initially uncharged, so it is allowing the flow of current. So it is basically initially behave short circuit. Short yani all current will pass through it. So this is the concept you will learn later on in more detail. So see now, what is RC time constant? So now we know that capacitor is fully charged. And I already told you, when the capacitor is fully charged, it can behave like a temporary battery. So let's see now what we are going to do. We remove the battery from here and the capacitor is fully charged. This is positive terminal, this is negative. Now, why it is positive? You go back in the previous slide and you will see. So the terminal which is connected to the battery is positive. You can see this one. So upper terminal is positive, negative is because of connected negative. That's why. So once it is fully charged, after some time, see, by the way, it is not going to be fully charged quickly. It is taking some time. you know that time. Okay, so time is this one. So this time is required to fully charge. Now when it is fully charged, we are replacing the source. We remove the source. Now we have this one. Now initially this is open. So open, so charge is still there. And how it is there? Yani initially. So now can you tell me what will be the initial value of the charge across the capacitor? Will it be large or will it be small?
Small.
Initial value large, right? So it should be now V initial. Yani initial voltage across the capacitor will be larger. And what will happen, girls, as I close this switch? It start, yeah, giving back the energy to the circuit, to the resistance already connected. So current will flow reverse direction and it will start giving the energy to the circuit. Let's see now. So from the start value, it is gonna be now reduced to 0. And also you can see as the current is flowing in the reverse direction. Can you see the direction of current flow now? It is counterclockwise. Previously that was clockwise. So we are using the sign here. Can you see negative?
Yes.
Yeah, so negative. Current will be very large in the beginning, but because capacitor is fully charged. But as the capacitor charge is decaying, so current will also decay in the circuit. And once the capacitor is fully discharged, current will also fully discharge, but the direction is counterclockwise negative. Is it clear?
Yes.
Okay, so these are the basic understanding of charging and discharging of the capacitor. Based on that, you have lab experiment also. So you must know this concept for the lab also, right? Now, see this one. Do you remember the pulse waveforms which I taught you in the previous chapter? Pulse waveform, correct? So
Yes.
these pulse waveform, you know, this is the time period, periodic pulses, right? So if I say its maximum value is 5 volt, minimum value is 0. So see now interesting thing. What is here? Yani at this time it is having high voltage, at this time it is 0, correct? 5, 0. Getting point? Yani what will happen? During this time, capacitor will charge. It is behaving like there is a 5 volt battery connected. When it is 0, yani it will behave like there is no battery here. So at that time, capacitor will discharge. Getting point? Charging and discharging will be happening with this duration. So this duration, capacitor charge, this duration, capacitor discharge. Charge, discharge, charge, discharge. Getting concept?
Yes.
Okay, now see. So here what we have VS, yani voltage, source voltage. Okay, then we have VC. And what is VC? Voltage across capacitor. Okay, let's see now. And this is what? VR. And do you know VR will depend upon IR? Am I right?
Yes.
And IR, you know that initially it will be clockwise, and the next step when it's discharged, it will be counterclockwise. Any positive, negative, positive, negative. So let's see now the waveforms when I close the switch. See, I close the switch. As I close the switch, what will happen? This is gonna be now continuous. This is going to be continuous charge and discharge. So if I draw the reference line for you here like this reference lines, huh? Now see. So this duration capacitor is charging, which is rising exponentially. And you know that the current will start positive current. This is maximum value, which is positive current here. So because current is positive, so definitely voltage will also be positive. So this is voltage. Okay, because and now as the current is reducing, current is reducing. So across this VR will also reduce. Current is reducing. So VR also reduce. So we are having this time VR. So it will also reduce. Now, this time, when this time come, so capacitor start discharging. This is the step. Capacitor voltage start discharging. And when it discharge, you know that current will flow negatively, right? Negative, counterclockwise. So when it starts flowing negatively, the voltage across VR will be start with the negative value. So this is showing negative value. So here it is gonna be negative voltage, and once the current becomes zero, so voltage across will also become zero. This is again, so once one cycle is complete, you can understand the second cycle consequent. It's gonna be same. So if I draw even current one, so current waveform is gonna be exactly same. I can also say it is IR. IR will also behave like that. So positive current will be up, negative current now showing downwards, any negative value. If we say this is the zero base. Clear to all? Charging, discharging shape. Okay. What now they are saying? What is the shape of the current curve? What is the shape of the current curve? Will it be exactly same or not as the VR curve? Okay, it is gonna be same because what we know, VR is equal to IR. And what is R? When we multiply by this one, R is just a constant value, okay, which is multiplying with the R. So the shape will gonna be same, okay, same as VR. We can reply to that one. The current has the same shape as the VR. All right, clear to all of you?
Yes.
Okay, so this is RC waveform understanding, and this is charging and discharging concept. So what it's saying, yani when it, okay, I think just stop now and we can have your okay questions. Just leave it here. So yani we stop here, but I will continue this one. Yeah. Okay, so what is the question now? Tell me.
Can we finish off the quiz at the end of the chapter because we didn't yesterday?
The quiz is simple and no question will come from the quiz.
Okay, how about we solve some questions from the book?
Whatever, tell me. Don't just tell me some. You tell me this one, then it will be easy, rather than if you leave on me. Because
Okay.
for me, all questions are very easy, but for you may be difficult. You tell me what you want. I can open it, okay? You tell me which question you want.
Victor, I have a question in chapter number 6.
Chapter number 6.
Yeah.
Okay, yeah, this is good. Now at least I can open quickly. So what do you want? Should I open the book or should I open what? The slide itself.
slide.
What slide? Okay.
Slide.
So I'm opening the slide quickly. No problem. I'm just opening one by one. So this is slide. Or and better than you just tell me the question. If you remember, you bring your questions. Okay, which slide number? Tell me.
42.
42. This one?
No. It's actually in your slides 39.
Okay.
Yeah, this one.
Mm-hmm. So don't you have the solution of this one?
I do have. Yeah.
Oh, okay. So what is your doubt here?
Doctor, can I share my screen because I have
Yes.
this.
Yes. Go ahead.
Here. I didn't understand this step. Why did we do this?
1 minute. Okay. So where this one?
Yeah, here.
Okay. So this is just I tell you how much will be the voltage across. So it's about the voltage across the parallel combination. What is that? Voltage across this parallel combination. How can I find the voltage here? I know this is the resistance, correct? I know the current because of -3. So if I multiply resistance by the currents, I can get it. How much is the voltage drop here across this parallel combination? Is it clear now?
Yeah.
And similarly, same here. I know this is the parallel combination. So how much is the voltage there? So I am just calculating resistance multiplied by the current, which is 3 ampere. This is the voltage. Now I can use these voltage to identify that how much is the voltage here, how much is the voltage here, because as I explained to you, this is the parallel combination voltage. So its mean is that the same -4 will appear across this one, same -4 will appear across this one, because they are in parallel. Correct? Did you get the point now?
Yeah. Okay.
Okay, so we can calculate the how much is the current here also. How can we calculate the current? Yani, I know the voltage, which is -4 volts. If I divide by this resistance value, which is 2, so -4 divided by 2 will give me -2 ampere. So I just calculate it. I am not focusing here because I am interested to know this one. Then I go for this one. And how much is the voltage drop across this combination? -2.25. So same voltage will be available to both of them. So -2.25 divided by 3 will give me this -0.7 volts. This is something which I explain here. Clear?
Okay. Yeah, I get it. Thank you.
All right. Okay. Yeah. Next. What is the next question, guys? Idea, Haifa, I already solved all the questions, all are idea. Main thing is the concept. If you have concept, inshallah, calculation is gonna be easy, but concept cannot be changed. Keep in mind, okay? So you need to practice your concepts. Calculation is gonna be easy as per the time is limited. So calculation you can easily calculate. But if you don't know the concept, what will you calculate? Yeah. What's here?
Here we want to find I for why we didn't take the R total for the whole circuit rather than for the branch.
No, what is your question? I didn't get you. Can you tell me again?
We want to find I for, right?
Yes, you need to find I4,
R
correct?
total we only take for this branch.
R total. Which R total? See, R total, if you go to R total, yani all 4 resistances will comprise of R total.
We will take I2, I mean, sorry, because it's apart from R2, right?
Yes, definitely, because we are not going to consider here I total. See, I total is here, which is coming from the source. Keep in mind, I total. So for I total, I need R total. But look here, is R4 directly splitting from the IT? No, I4 is splitting from the I2. I2 is now dividing into 2 parts here, you can see. So I need I2. I need I2. It is a part of I2. So how can I find the I2? This is the concept here. So you can apply current divider rule simply if you know I2. If you want to know IR4, you know the current divider rule. It says I4 will be equal to the opposite resistance, yani R3 over R3 plus R4 multiplied by I2, which is the total current for this, because I2 is dividing. Clear? Okay. Is it clear?
Yes.
Okay, next.
Doctor, when we use the general current divider rule and the specific one?
Oh, what's that again? Current divider rule.
When do we use the general one and the specific one?
See, this is actually current divider when we have two resistance in parallel. This is the rule. Understand?
Yeah.
This is the general. And if you go for the general, which is Ix, any current in any branch, is equal to what is gonna be? It is gonna be what? RT over Rx multiply by what? I total. Yeah. So this now, this general rule, now, you may have now many resistances connected in parallel. So you have to find their total. And you know how to get the total of resistances when they are connected in parallel. So got it this way and then apply this one. So you can calculate the current in any resistance. This is the way.
So also in this example, we can use the general formula, right?
Why not? You can use this one here. Same thing. Use the general here. Or who is stopping you to use the general? Calculate the R total here. So what is the R total here? You see these two resistances are connected in parallel.
Yeah.
So what is the R total? Will it be R3, R4 over R3, R4?
Yeah.
Plus R4. Correct or not?
Yeah, correct.
Okay, so just put it this one there. And what is your Rx? Can you specify? Is it R4, correct? R4 multiply by IT. So R4 will cancel this R4 and you will get the R3 over R3 plus R4 multiply by IT. Is it not the same?
Yeah, it's the same.
This is very basic thing. You should clear, chapter 3, but now you are clearing. No problem, never late. So this is something. When I explained this thing, I remember that time. No problem. Yeah. Now, Manar is saying, why don't you take R1? Manar, R1 is not in the picture. Why should I take R1? R1 is not here. R1 is out here. And I am interested to calculate the current here rather than I1. So we will discuss here or here. So I'm discussing here. I2 is splitting into R3 and R4 like that. Okay, and next question. Time is short, so better come to the question. Now clear this one?
Okay, doctor, can you calculate I4 by getting the volt?
My dear, when I solve this question, I remember I solve it 3 different ways, 4 different ways. You can apply whatever you want.
Okay.
I told you this one, okay? It's not necessary you just follow what I said. You can calculate I1, then after that you can apply voltage divider. So there are a lot of ways. You just check my lecture at that time. I try 2-3 ways to solve this one. So you apply anything, no problem. Okay? You are not restricted.
Okay.
Yeah. Yes, next question. So don't restrict yourself. You can calculate in any ways, whatever you want. You can apply voltage divider, current divider, whatever. Yeah, next question.
Doctor, how many nodes are in this circuit?
How many nodes? Okay, so you can see this one node is there. This is complete one node. Okay, one node is this one down. Okay, one more is here. So how many? A, B, C, 3 nodes. How many branches now? Yes, 1, 2, 3, 4. Bus. Yes. Yeah. Next. No question now. You people asking that we have questions, we have question. And now no one is asking question. Because you did not study, I think maybe for the exam. Okay, think quickly. I'm taking your attendance. What are your questions? Your group will be not getting chance before Monday, you know that one. So better you ask the questions. Even if any from any book, you just tell me any question. But if you say teacher saw some question from the book which is similar to the, this is something like for me, all questions are good. I can open any book. So you tell me from your side, which is you want, which one is you feel it is difficult for you. That will be more, good. Think I am just going to take your attendance.